Good morning. Good morning. Okay. That's good. I want to keep it going. So last class, so far we were able to talk about reversible systems, and that if the system is in a closed system, uh, the reaction can go forward and go backward. Once the rate of forward and reverse reaction are equal, then we have reached an equilibrium. One characteristic of equilibrium is equilibrium constant, a numerical value that talks about what's going on in the system. The equilibrium constant is the rate of the forward reaction rate constant over the rate of the reverse rate constant, which is given as concentration of product over concentration of reactant. We can also express it in terms of pressure, and this is the relationship between equilibrium in terms of concentration and in terms of pressure. Now let's work some examples. The reaction for the formation of nitrosyl chloride is as given as 2NO going to plus Cl2, all in the gaseous state, giving us the nitrosyl chloride. This is the nitrosyl chloride. At 25 degrees, the pressures at equilibrium were found to be 1.2 atmosphere. Oh, I think we solved this question last class. Yes, we solved this question last class. The next question to solve, this one involves something called ICE, initial concentration, change in concentration, and equilibrium concentration. This can also be found in your note. Okay, 1 mole of iodine and 1 mole of hydrogen are mixed and allowed to reach equilibrium. The amount of hydrogen iodide present at equilibrium is 1.5 mole. Calculate the equilibrium constant. Remember, to calculate equilibrium constant, we need to use equilibrium values, equilibrium concentrations. Concentration can be expressed in terms of pressure. It can be expressed in terms of mole fraction. It can be expressed in terms of number of moles per volume. Okay, so the equation for the reaction is given as H2 plus I2 to give HI. The equilibrium constant for this expression, product over reactant, in terms of Kp is pressure of Hi raised to power 2 because of these two, divided by pressure of H2 raised to power 1 because is only 1 mole, and also divided by pressure of iodine raised to power 1 since there is only 1 mole. And again, pH2, Pi2, and pHi are equilibrium partial pressure. This must be partial pressures measured at equilibrium. However, we're given 1 mole and 1 mole, that is initial concentrations. Okay, so we construct what we call the ICE table. ICE again means initial concentration or initial amount. Change C means change in amount, so that's the change observed to reach equilibrium. And then E is equilibrium amount. So this is our table. The table contains the ICE in rows. So we want to fill it out. So in the table, each column stands for all the species present in the reaction mixture. So if we add more than H2, I2, and HI, and if we add other species, we will construct, we'll have an extra column. So initial amounts, as given from the question, there's 1 mole of iodine. So we write it 1 mole of iodine. That is the initial amount of Hi2 that's present. And 1 mole of hydrogen. So the initial amount of hydrogen that is present, that is allowed to reach equilibrium, are allowed to reach equilibrium at 1 atmosphere. That's the total pressure or the external pressure. Initially, it was just hydrogen and iodine that was allowed to reach equilibrium, which means Hi was 0 moles. So at the initial condition, initially 1 mole of H2, 1 mole of I2, and 0 moles of Hi. So that's initial conditions. However, the amount of hydrogen iodide present at equilibrium was observed to be 1.5 mole. So we have 1.5 mole at equilibrium. So what we need to do now to calculate this expression is to determine the number of moles of H2 present at equilibrium and number of moles of I2 present at equilibrium. That's what we need to do. So initial concentration and at equilibrium, that's what we just described. Anyway, so what we can say is that before this comes out, so let's pay attention. The total number of moles from going to 0 to 1.5 is positive 1.5. So usually the equilibrium amount E is usually equal to the initial amount for reactant minus change minus C, and for product it will be I plus C. So this is let's ignore this for a moment. So this is going from here. The change has increased by 1.5. So we write 1.5 here. So if 1.5 mole has been created by 1 mole, then what's the change in the amount of moles of I2? So 1.5 moles have been created by change in the amount in HI. So the change in the amount of H, we look at the stoichiometry of the reaction, 1 mole of H2 is equivalent to 2 moles of HI. If that's the case, 1.5 mole of HI will be equal to how many moles of H2? So let's say X. So X will be equal to 1.5 times 1 over 2. That's when cross multiplying, and this will give us 0.75. So 1.5 moles of HI will be produced by 0.75 moles of H2. Similarly, Since you have 1 mole producing that, 0.5 moles of H2 will also be provided. So that's what we have here. Delta HI, the change is that, so which means change in H2 will be 0.5, change in I2 will also be similar because you have 1 mole. So this is for H2. Similarly, 1 mole from reaction of I2 is equivalent to 2 moles of HI. Therefore, 0.5 mole of HI will be produced by, if we call this Y will still be the same thing, cross multiply, Y equals to 1.5 times 1 over 2, which is 0.575. So 0.575 moles of HI2 has also produced 1.5 moles. Anyway, so let's continue to fill our table. So this has changed by 0.5. This has changed now by 0.75. But this one is a reduction, so we have minus. Also, this has also changed by 0.75. And also, being that it is a reduction, it is negative. So what is left at equilibrium will be 1 minus 0.75, which is 0.25, and similarly 0.25. So the complete table is as given. Let me see if we have any questions so far. Okay. So now let's calculate our equilibrium amount. Always calculate Kp at equilibrium amount. So equilibrium amount is 0.25 mole, 0.25 mole, and 1.5 mole. Bringing this to a different slide. So equilibrium amount 0.25, 0.25, 1.5. Now, mole is not concentration. Concentration is reported in number of moles per volume, partial mole fraction. Yes, it's also reported in mole fraction. So since we are working in mole, the partial fraction A of a substance is, sorry, the partial pressure, not partial fraction, please. The partial pressure of a substance A is given by the mole fraction times the total pressure. The mole fraction, XA, is mole fraction. The mole fraction is defined as the total number of A over total number of moles of species. In our closed systems, in our closed system, we have hydrogen, I2, and HI. At equilibrium, we have 0.25 moles of hydrogen, 0.25 moles of iodine, and 1.5 mole of HI. So in our equilibrium mixture, that means we have 0.25 plus 0.25 plus 1.5. That's a total of 2 moles. So the total number of moles of all species present is 2 moles. So the mole fraction, so knowing this, we can calculate the mole fraction of H2, calculate the mole fraction of I2, and calculate the mole fraction of HI. Once we calculate the mole fraction of H2, we can calculate the partial pressure of H2, which will be its mole fraction of H2 times the total pressure. So that's a concentration unit when dealing with pressure. So the mole fraction of H2 is 0.25 divided by 2, which is the total number of moles. And this gives us the partial pressure, which is XH2 times P total. From the question, the P total is 1 atmosphere, and you have 0.125 atmosphere. Similarly, XI2 is given, and the mole fraction of H is 0.75. Therefore, we can calculate our equilibrium constant now, which is equilibrium constant Kp, which is P, okay, P pressure of Hi. Recall this is the reaction H2 plus I2 going to 2Hi. This is supposed to be 2. So this is pH2 squared over pH2 times pI2. We're slotting the value of pH, pHi, 3.5 squared, we get 36. Okay. So moving on. No question. Any question? No question. So there's some other worked examples on the slide. But because of time, we will not be able to go through with all of them. So we'll continue discussing the characteristics of the equilibrium constant. So for those of us following with our slide, if you have printed your slides out, so I'm on page 12 of the slide 26. If you're following with the notes, around page 14, 15. Oh, I thought this one was animated. So some other features of the equilibrium constant. Oh, sorry. We looked at this yesterday on Monday. Okay. Some other features. If you reverse a reaction, for example, N2O4, this is a reversible reaction, and we have written the equilibrium constant expression for this forward as NO2 squared over N2O4. If you reverse the equation and you have N2O4, remember, you can achieve equilibrium from either direction. If you reverse the equation or the expression, and then you now have NO2 on the product side, on the reactant side, you notice that we have reversed the equilibrium constant. So the equilibrium constant for a reaction in a reverse is a reciprocal of the equilibrium constant for the forward reaction. So if K equals 0.212, that means that our K reverse of the reverse equation will be equal to 1 divided by the reciprocal of 0.212 and is given us as 4.72. That's number one. Number two, the equilibrium constant of a reaction that has been multiplied by a number is the equilibrium constant raised to the power that is equal to that number. For example, you have our expression N2O4 plus going to 2NO2, same reaction from here. That's the equilibrium constant. If you consider multiplying this by the whole expression by 2, so you would notice that this is simply equal to NO2 squared over N2O4 everything squared. So that's equilibrium reaction squared for the first one. The equilibrium reaction constant for a net reaction made up of two or more steps is the product of the equilibrium constant for the individual steps. So consider you have this reaction CO plus H2 to form CH4 plus H2O. The equilibrium constant expression is CH4 times H2O divided by CO times H3 raised to power 3. And this other reaction, so this is equation 1, that's equation 2. Also, this is the equilibrium constant expression CS times H2 raised to power 4 divided by CH4 times H2S raised to power 2. If we add these two equations together, equation 1 and equation 2, so let's see, CO here, H2S, so H2, the H2 should come to the reactant side, but we have 4 moles of H2 here, so it cancels out. And you have 1 mole, so this is 4 minus 3, so you have excess of 1 mole on the product side. More on the reactant side than 2H2S. So going to CH4, so there's CH4 here and CH4 here, so that cancels out, so there's no more CH4. Plus H2O, H2O is still there, plus CS2, so we have CS2. Is the equation balanced? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. 2S, 2S. C is 1, okay, so equation is balanced. Equation constant expression for this reaction is that of CS2 times H2O times H2 divided by CO times H2S raised to power 2. Now, if you consider this equilibrium constant multiplied by this equilibrium constant, this is CH4H2O over COH2, CS2H2 over CH4H2S. Of course, so CH4 cancels out. There's H2, so H2, 3, so you have 1 here now. So you have H2OCS2, H2, which is equal to that. So the equilibrium constant for a net reaction made up of 2 or more steps is the product of the equilibrium constants of the 2 reactions. For example, you are given this reaction HF and CO to determine the value of the equilibrium constant for this other expression. So now if you inspect the 3 reactions, you would notice that there's a relationship between the addition of these 2 reactions, equation, let's call this 1, call this 2. So there's a relationship between 3 and the sum of 1 and 2. So you have HF, so this is multiplied by 2. H plus, we don't have H plus in here, but it can be cancelled out by this. Then F minus is still here. H2, reactant and product side. So manipulation, from what I can see, let's multiply the first reaction, equation 1 by 2, because so that we can end up with 2HF on this side, much like we're dealing with thermochemistry and acid law. So if you multiply that, our K equilibrium is raised to that power because you multiply this by 2. So we get this. So comparing equation 3 with equation 2, I noticed that H2O, which is on the product side, which is on the reactant side in equation 2, is on the product side in equation 3. C2O4, which is on the product side in equation 2, is on the reactant. So it suggests to me that we need to flip the reaction or reverse reaction 2. So if you reverse reaction 2, then you have C2O4 on the product side, H plus on the reactant side. And this gives us that we need to find the reciprocal of the given K equilibrium. Reciprocal is 1 divided by the original value. So that gives us that. So looking at this, you see the product is even more now. So now let's compare. So let's call this equation. So this is equation 3, this equation 4, equation 5. Equation 4 compared to 5. So we have 2H, 2H now. 2F on the product side, 2F on the product side. We all still need to just deal with 2H plus. We compare equation 5 with 3. 2H plus is not here, so we'll come back to that. C2O4 is on the reactant, H2. Okay, so if we now compare 4 and 5 in relation to 3, we notice that it's the H plus that needs to go. And since it's on the reactant product side on equation 4 and reactant, we know that once we sum up those two equations, these equations 4 plus 5, we arrive at 2HF plus CO2 going to this, so which is what we have here. We use the new equilibrium constant, so the equilibrium constant for this one will be the K equilibrium. So equilibrium constant for this reaction will now be K equilibrium for reaction 4 multiplied by K equilibrium for reaction 5, which is what we have here. Three new messages, no question, no question, no question. Okay. Okay. So more questions, more examples for you on the slide. Let's talk about heterogeneous equilibrium. Heterogeneous equilibrium involves more than one phase. So that's equilibrium with more than one phase. So when we're talking about phase, we are talking about solid, liquid, aqueous, and gas. So these are the phases that we are talking about. So if your equilibrium involves only solid, it is homogeneous equilibrium. If it involves only liquid, it's homogeneous equilibrium. If it involves only aqueous solutions, it is homogeneous. If it involves only gases, it is homogeneous. But once it involves more than any of these, we call it heterogeneous equilibrium. An example is the dissociation of lead chloride, which is an insoluble salt, in water. Some of it dissolves into iron as Pb2 plus and Cl minus. And you still have the solid PbCl. Another example is the decomposition. I've been learning about this for a very long time. Decomposition of calcium carbonates. Carbonates generally decompose to give oxide plus CO2, which is one of the experiments that you will carry out in the lab soon. The equilibrium constant expression for these two reactions are given as this. So equilibrium constant does not include pure liquids and pure solids. So pure liquid is not aqueous. Aqueous is a mixture of something, is something dissolved in water. It's not pure liquid. Pure liquid is everything liquid. H2O liquid is pure liquid. C2H5OH liquid, that's pure liquid with nothing else added. That's what we mean by pure liquid. And why is this so? And for the so the equilibrium is only the ones that are aqueous or gases. Similarly, the equilibrium for the second one, this is a solid, this is a solid, this is gas. That's because over time, now the position of heterogeneous equilibrium does not depend on the amount of pure solids or pure liquids. The experimental results of heterogeneous equilibrium, please note that heterogeneous equilibrium. In advanced cases, you might see that when you're dealing with pure liquids of different forms, and especially when you now start to deal with number of moles, the equilibrium constant may, in the slightest form, depend on the amount. Never, but we're talking about aqueous now. Sorry, heterogeneous. And why is that so? The concentrations of solids and liquids are essentially constant. Why are they constant? It's simply because in our activity definition, the concentration is density over molar mass, and that for a solid, for both, so concentration for solids and liquids, you can only look at them in terms of density per molar mass. That will still give you mole per dm cube. So that's for pure solids. And this concentration remains constant throughout, so regardless of whatever it's still just the density, regardless of what you're dealing with. So you're dealing with a constant divided by a constant, it remains constant. So you only have the CO2 for this expression affecting the equilibrium constant. So as an example, let's look at this. What are the equilibrium constant expression for this? Let me see, are there questions? Let's go to deal with questions. Okay. For example, so equilibrium constant expression for this one, SNO2 is solid gas. So this will just be CO2 raised to power 2 over CO raised to power 2. Second one, so zinc will not be included, copper solid will not be included, so you have zinc plus over copper plus. Here, it's H2 squared plus O2. Now, this is pure liquid. And in the last case, we have H2O2 because we now have a gas here. So please note the difference between these two. More basic concept before we talk about some applications. How do we know that a reaction is in equilibrium? There's something called a reaction quotient, which is a number obtained by substituting the reactants and products or partial pressure concentration at any point during the. So this is used to determine whether you have achieved equilibrium or you are past equilibrium. So you see the expression is the same thing for the reaction AA plus BB going to CC plus DD. This is the expression for the reaction quotient. It is the same raised to power. It is the same as expression for equilibrium constant, except for these small zeros that we have there to indicate that we are talking about just a random concentration. So this is calculated at using concentrations that are not necessarily at equilibrium. So three things may happen. You can have Q less than equilibrium, Q less than equal to equilibrium. Okay. So what this means that if you want to determine Q, you're only comparing it because you know what the value of K equilibrium is. So when Q is less than K equilibrium, then it means that you have not, you still have to produce, the concentration of product is too small and that of reaction is too large. So when Q is less than equilibrium constant, you need to produce more products. You still need to go right. When Q is equal to the system is in equilibrium, you don't need to do anything. When Q is greater than equilibrium, then you know that you need to shift your equilibrium to the reactant side. So this is a diagram to say that when Q is less than K equilibrium, you shift to the right, that's to the product. And this is to the left, which is to the reactant. Okay, take the time. So that we can talk about factors affecting equilibrium and equilibrium constant. Anytime we have pure solid and pure liquid, yes. Question. So anytime we have pure solid and liquid, we won't add it to the expression. That is correct. Any other? Okay. So for the synthesis of ammonia, this is the favorite way to, most common way to produce ammonia at equilibrium at 500 degrees centigrade. It's always important to talk about the temperature. The equilibrium constant, K equilibrium, is 6.0 times 10 raised to power minus 2. We do not include the units of the equilibrium constant. So the question is, now you are trying to produce ammonia. You already know what it is at that temperature. You want to know whether you have reached equilibrium, you have produced enough ammonia. So whether you want to get out ammonia out of the system so that you can produce more, you sample your system. And these are the conditions. Predict whether the direction in which the system will shift to. And these are the conditions that you find. So in order to predict, we need to calculate equilibrium reaction quotient for each one. So in the first case, substituting the values of the concentrations given, we have 1.37 times 10 raised to the power 7, meaning that Q is greater than equilibrium. Because Q is greater than equilibrium, it will shift to the reactant side. In industrial applications, it means that you can actually take off some nitrogen if you have too much product in the system. So that's what the other slide showed the other time. K greater than equilibrium means too much product. So if you are looking to produce too much product, you can just remove some product. I hope I've not confused us. In the second system, K equilibrium, so Q is 6.0, which is almost equal to the equilibrium constant. So the system will not shift. In the third instance, plotting in this value, this is what we observed. This is less than K equilibrium, and the system will shift to the right. So to the right will be to the product. You have too much reactant in the system. Okay, let's look at factors affecting equilibrium and equilibrium constant. So equilibrium is the state in which Rf is equal to Rr from reactant to product. What can affect this? Equilibrium constant on the other one is the numerical value telling us, relating us the concentrations that we have in the system. There's this thing called the Le Chatelier's principle. I'm sure this is not the first time you're hearing it, that states that if you disturb the equilibrium, either by changing temperature, pressure, or concentration, the system will shift in a way to counter the effect of the disturbance. There are so many ways in which you can say it. If you disturb, system adjusts itself to counter that effect. What can affect the equilibrium? That's pressure, concentration, temperature. What can affect equilibrium constant? Only temperature. So let's look at them one after the other. Factors that affect equilibrium positions. Concentration, the first one, there are three of them that we said. Concentration, which means amount of substance. So if you change the amount of any of the species, the system will react to produce what you have taken. So if you increase the amount, the system will react to consume it. If you reduce the amount, the system will react to produce more. So if a substance is added to the equilibrium, the system reacts to consume some of the substance so that equilibrium can be achieved. Equilibrium is balance. So it's even a mechanical equilibrium. Once you try to put weight on one side, just imagine somebody walking on a rope. Once there's too much weight on one side, the person bends to counter the effect of the excess weight. So if a substance is removed, the system reacts to produce more of the substance. For example, our famous Haber process in trying to produce ammonia, this is our equilibrium constant. So N2 or H2 is they are both reactants and they would have the same effects in terms of concentration. So if the concentration of the reactant, which is N2 or H2, is increased, if it is increased, so increasing this, it will shift to the product side. If this is increased, it will shift to the reactant side. So if H3 is increased, it will have the same effect as reducing H2 or N2. So in general, for a reaction at equilibrium, the forward reaction is favored by an increase in concentration of the reactant, which is if you increase this, or if you reduce this, it will go, or a decrease in concentration of the product. And the backward reaction is favored by an increase in concentration. So the reverse reaction, increase in concentration of products. Because when you add products, you want to quickly consume it. And when you consume the species, you are producing the other species. Now let's look at pressure. Pressure effect is only observed with systems involving gases. That's because if you look at the three classical states of matter, solid, liquid, and gas. Okay. Only gas is the one that is highly compressible, so it is the one that pressure affects. And you can change the pressure by either removing or adding a gaseous substance by changing the volume of the container. If you change the volume of the container, volume and pressure have an inverse relationship, or by an inert gas, so that you can have different mole fractions. However, inert gas does not affect the concentration or partial pressure, so no effect on equilibrium. Anyway, so how does pressure affect equilibrium? First thing you have to notice the relative number of moles of the reactants compared to that of the products. The higher the number of mole, the higher the pressure can exert. So we'll look at an example. So you need to look at AA plus BB going to CC plus DD. Now so we're looking at A plus B relative to C plus D. Now, whether pressure affects will depend on this stoichiometric relationship. But one thing that you have to notice, an increase in pressure will favor the side with fewest number of moles, and a decrease in pressure will favor the side with the highest number of moles. So let's look at an example. Consider this gaseous reaction. This is a homogeneous reaction, G plus P plus going to G. The number of moles on the reactant side, there's 2 moles of SO2 and 1 mole of, so we have a total of 3 moles of them. So this kind of reaction, gas pressure change will affect it. So we have a smaller number of moles on the product side. So if we increase pressure, that means we make the volume smaller. If you increase pressure, the reactants with the number of moles with the side with the smaller number of moles would be favored. And why is this so? Imagine if you want to reduce the volume, so you need to have smaller number of molecules in the system. It's when you increase the system that you have enough space for things to move around that you would have more particles. So increasing favor, if you increase the pressure for this one, increasing P favors SO3 and reducing the pressure. So if you look at this, so favors SO2 plus O2. Consider it this way, increasing the pressure means reducing volume. Okay. Also, let's look at this reaction. Reactant side, 1, product side, 1 plus 2. So if you increase, so in this case, this is 1 and 2. If you increase pressure, which is equivalent to reducing the volume, PCl5 is favored and the reverse reaction is favored. If you reduce the pressure, meaning more space, or increased volume, then the product will be favored. As the last example, CO2 plus H2, I think this is called the Bosch process or the reverse Bosch process anyway. Giving CO plus, so we're looking at how many number of moles? 1, that's a total of 2. Here it's also a total of 2. So if you increase pressure or reduce pressure, no shifts in equilibrium is observed. Why? Because you have the same total number of moles on both the reactant and the product side. Okay. So let's look at temperature. So we said temperature changes the position of equilibrium. In addition, it also changes the equilibrium constant. How do we look at it? We need to consider the delta H of the system. Delta H is the change in enthalpy. So this is what we studied in thermochemistry. Under that, looking at delta H, so we want to know whether a reaction is endothermic or exothermic. So let's consider this. Consider the Haber process. So this is an exothermic reaction. The forward reaction is exothermic. Let's put it that way. Because when you say something is reversible, which of two reactions are taking place? So this is an exothermic reaction, which we can also write like this: N2 plus 3H2 going to 2NH3, and delta H is minus 92 kilojoules. So because the forward reaction is exothermic, one of the products is heat. So forward reaction is exothermic, and necessarily the reverse reaction is endothermic. So one of the products is heat. So if we increase the temperature of the system, is equivalent to increasing the concentration of a product. So if we increase the temperature of the system, which is equivalent to increasing products, so let's see, N2 plus 3H2 plus 2NH3 plus heat. So increasing heat means that we are increasing this, so the reaction shifts to the left. If we reduce the temperature, it means we are taking off heat. We're taking off heat and the reaction shifts to the front. Anyway, so before we move, what happens to the equilibrium constant? If we add heat, let's still it's increasing the temperature, because addition of heat means increasing temperature. So reaction shifts, equilibrium shifts to the left, meaning more of NH3 is consumed. So we're still looking, so more NH3 is consumed. So if more NH3 is consumed, the concentration, apologies about that, concentration of NH3 reduces. And if it reduces, let's look at the equilibrium constant. Let me write it clearer. This is the equilibrium constant. I just want to write it again. K equilibrium, there's something coming there. K equilibrium is NH3 squared over N2 H2 cubed. So if this is reduced, it means that the product, the numerator becomes smaller. And if the numerator becomes smaller and this becomes bigger, the value of K equilibrium will reduce. For the next example, any question? Okay. If we look at the other example there, the composition of calcium carbonates. The composition of calcium carbonates, the forward reaction in this case is endothermic, and the backward reaction is exothermic. That's because we need heat. So endothermic reaction, you supply heat to the for the reaction to take place. This is our K equilibrium. So this something different is the addition of heat in this case now is the same thing as adding a reactant. So if you add a reactant, it means that more of CaCO3 is consumed and its concentration reduces. If CO3 reduces very fast, CO2, this implies that we have more CO2. So if more CO2 is produced, then K equilibrium increases. So in general, if the temperature of a system is increased, the system reacts as if we have added reactants to an endothermic system or a product to an exothermic part of the system. And K equilibrium will also change. It will change depending on the system that you are looking at. One thing to just quickly say, because one of the factors that affect the rate of a reaction is a catalyst, in addition to the three other ones that we have said. However, a catalyst does not affect equilibrium. It only helps you to achieve equilibrium faster, but not the equilibrium itself. Okay, so there's some questions for you to work there. On Friday, we will talk about applications to solution. I think I will send the slide ahead. Any question, please? No question. It's 12:59, so we have time. Okay, so no question. I wish you all good luck.